The Role of Algorithms in Computing, Bucks County Community College. I'm John Summers. Algorithms. An algorithm is any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. An algorithm is thus a sequence of computational steps that transform the input into the output. An algorithm is a tool for solving a well-specified computational problem. A sorting algorithm rearranges the sequences of integer key values into ascending order. So we have A1 followed by A2, followed by A3, followed by an-1, followed by a to the n. And as output, we have A1 prime, A2 prime, A3 prime, an-1 prime, and an prime, where A1 prime is less than A2 prime, less than or equal to A2 prime, which is less than or equal to A3 prime, which is less than or equal to n-1 prime, which is less than or equal to n prime, a to the an prime. And the input sequence is called an instance of the sorting problem. An instance of a problem consists of the input satisfying whatever constraints are imposed in the problem statement required to compute a solution to the problem. Sorting is a fundamental operation in computer science. There are a large number of sorting algorithms. Which particular algorithm is the best depends upon several factors: the number of items being sorted, the extent to which the items are already somewhat sorted, possible restrictions on the input values, item values, the architecture of the computer, the kind of storage devices to be used, main memory, disks, tapes. An algorithm is said to be correct if for every input instance it halts with the correct output. The algorithm solves the given computational problem. An incorrect algorithm might not halt at all on some input instances, or it might halt with the incorrect answer. And even incorrect algorithms can be useful if their error rate can be controlled. An algorithm can be expressed in a natural language such as French, as a computer program, or even as a hardware design. Such specifications must provide a precise description of the computational procedure to be followed. What kinds of problems are solved by algorithms? We have the Human Genome Project, we have the Brain Initiative, we have the Internet, we have electronic commerce, manufacturing, logistics, longest common subsequence, topological sorting, finding the convex hull of endpoints in the plane. And you can see that illustrated here in the figure at the right, in which we have bounding vertices that contain all the other vertices. What do algorithmic problems share in common? Many candidate solutions, the overwhelming majority of which do not solve the problem at hand. We also have practical applications, such as computing the shortest path amongst vertices in a directed weighted graph. And not every algorithmic problem has an easily identified set of candidate solutions. For example, a Fourier transform, converting the time domain into the frequency domain. Data structures. A data structure is a way to store and organize data in order to facilitate access and modifications. No single data structure works well for our purposes, and it is important to know the strengths and limitations of a variety of data structures. Technique. It's possible to encounter an algorithmic problem for which there is no published algorithms. This class covers algorithm development, and we're going to look at the way algorithms work. We'll also look at describing the efficiency of algorithms, and by studying existing algorithms, we're going to build upon a knowledge base that makes it possible to design and implement algorithms for new implementations. And there are hard problems, non-deterministic polynomial complete problems, or NP-complete. No efficient algorithm is known, and the only resort is brute force. And if an efficient algorithm is found to solve one NP-complete problem, then efficient solutions exist for all NP-complete problems. And there are several NP-complete problems that are similar to problems for which there are efficient solutions. So there's kind of a light at the end of the tunnel. If a problem can be shown to be NP-complete, then there may not be a perfect solution. And this is where brute force may enable an adequate but imperfect solution. And an approximation algorithm is an example of an imperfect solution. The shortest path problem is NP-complete. There is no ideal solution. Parallelism. Processor clock speeds have been increasing at a steady rate for many years. Because power density increases superlinearly with clock speed, chips run the risk of melting once their clock speeds become high enough. Multi-core processors enable parallel processing. These processors are essentially several sequential computers on a single chip, a parallel computer. Algorithms are best designed with this parallelism in mindset, and such algorithms are regarded as multi-threaded. Algorithms as technology. Even if computers had no limitations, algorithm design would still be important. There should be assurance that the algorithm terminates with the correct answer. Documentation goes along with design. Algorithms should be efficient in terms of time and space. Efficiency. The insertion sort and merge sort are described as having time complexity related to the number of items being sorted. Insertion sort takes C1 times n squared steps given n items. Merge sort takes C2 times n times log base 2 of n steps given n items. The constant factor has much less influence on running time than n does. The bigger n gets, the more merge sort outperforms insertion sort. Efficiency. Imagine two computers, A and B. A has a faster processor than B. What happens if we run insertion sort on computer A and merge sort on computer B? Which computer will complete the sort more quickly? Suppose that A executes 10 billion instructions a second and B executes 10 million instructions per second. Computer A is 1,000 times faster than computer B. B outperforms A. In general, as the problem size increases, so does the relative advantage of merge sort. Algorithms and other technologies. It made good sense to regard algorithms as a technology, just like hardware. Advanced computer architectures and fabrication technologies, easy-to-use, intuitive graphical user interfaces, object-oriented systems, integrated web technologies, and fast networking, both wired and wireless. Artificial intelligence is built utilizing a wide variety of algorithms to do such things as finding the shortest path. Hardware design requires the utilization of algorithms. GUIs rely upon algorithms. Routing and networks relies heavily upon algorithms. Compilers, interpreters, and assemblers make use on an extensive basis of algorithms. And it is at large problem sizes that better performing algorithms make a tremendous difference.